Good evening, everybody. So, today we will just talk with the mechanisms where we can see that how a particular complex formation reaction is taking place with the formation of at least one metal ligand bond. So, the second part of these reaction mechanisms will be considering on the equilibrium formation of the complexes. So, when we add metal ion and the ligand to each other, we find that the corresponding metal ligand bond is formed, and depending upon its corresponding coordination number requirement of the metal ion, if the metal ion present is in some oxidation state, say +2 or +3, and if it binds to say 6 ligand groups, and these ligand groups will occupy the metal ion at 6 different positions in a 3-dimensional array, and if these 6 positions are occupying a particular octahedral geometry, we get a corresponding octahedral complex. And depending upon these, that means if we can have, so this in the first step, if one M is reacting with one L, we are getting Ml species forming, but what actually happening, it is basically nothing but some sort of ligand substitution reactions, because we all know now that whenever a metal salt is available in the solid state, and if we dissolve this metal salt in aqueous medium, that means water is given over there. So, we get the corresponding hexaco complex immediately. So, this reaction is very fast, and sometimes it is very difficult to monitor this very fast reaction, but when we get some different metal complex apart from this hexaco compound, which is always present in solution of water, we use these ligands. So, this L is given. So, one after another, that means all 6 water molecules will be replaced by these L groups. So, they are all replaced, and basically what we get there is the corresponding ligand. That means one particular ligand was water molecule, and that water molecule will be replaced by the new ligand L. It can be ammonia, it can be ethylene diamine, or it can be any other sulfur bearing or any other type of ligand. So, we get a ligand substitution reaction. And for such 6 ligands to occupy 1, 2, 3, 4, 5, 6, we get therefore all 6 steps. So, all 6 steps we can have, and ultimately we can have a corresponding Ml6 species. So, if we can monitor the corresponding concentration of either the free metal salt or the aquo complex in solution, and if we know the corresponding concentration of the ligand, we all know that the equilibrium constant for the formation or the equilibrium formation constant K can be found out. So, that we also know that depending upon the nature of the ligand and its corresponding chelating behavior, if they are chelating, the stability constant of the metal complexes. So, this K we get as the corresponding equilibrium constant, and if that particular K, which has some relation with the corresponding thermodynamic stability of the complex, we consider it as the corresponding compound is stable if the K value is pretty high. That means what we can find out, we will find out the concentration of the metal complex formed. If this compound, because most of these cases what we study in these octahedral complexes of Mn plus is the corresponding metal complexes of transition metal ions. So, if this is a transition metal ion, that means that particular transition metal ion would be colored, and if we can monitor the corresponding formation of this Ml or Ml6 compound by looking at the corresponding lambda max value for the formation of this particular MLS species and its corresponding epsilon max, the molar absorptivity of that particular compound. So, we can find out this corresponding concentration of this ML6 species, concentration of the M is known, and concentration of added L is also known to us. So, that gives rise to the corresponding equilibrium constant. So, equilibrium constant tells us that how the stability of the corresponding compound is forming due to the corresponding ligand substitution reaction by stepwise replacement of all the 6 water molecules by these ligands. So, when we consider this as the equilibrium formation of these complexes, the reaction mechanism will not tell us how quickly they are forming, that how quickly the equilibrium is achieved for the formation of this particular ML6 species. So, we will just utilize something what we consider as the rate. That means the rate of the reaction at which, whether the rate is very fast or the rate is very slow, at what particular rate the metal ion is reacting with the ligand. So, the rate is important in understanding the corresponding mechanism and the chemistry of these transition metal complexes. So, in particular case, if we just consider that if we want to understand the corresponding electronic structure at the same time and the involved intermediates. So, if this ML6 is forming over there, so the other steps what we have utilized is the corresponding stepwise replacement of the water molecules by L. So, these species we can consider as some intermediates also. So, if they are our intermediates, then how the intermediate is achieved, and through that intermediate how the ultimate product or the final product is formed, that we can find out. So, the explanation for any reaction, if we consider the corresponding reaction coordinate, that means the free energy change for the reaction, which will also tell us about the corresponding free energy change, because this K value, the equilibrium constant value, is dependent on the corresponding free energy change for the reaction. So, if we have the free energy change for that particular reaction, so if we have the free energy change along this axis and the extent of reaction on the other axis, and if we just consider that the reaction is approaching through this path where MH2 or Mx is there, that means Mx is reacting with Y, Y is nothing but our L, X is nothing but our water molecule. Then at this particular point we have a stabilized part, and if this particular stabilized part is can be detected, so we have the corresponding stability of that intermediate. So, intermediate has some sufficient stability what we can measure, and in this particular case whether Mx plus Y or My directly can form over there, that tells us how quickly this intermediate is formed, and then we have My plus X ultimate product, that means Ml6 is forming. So, this particular case, that means the amount of activation what we get from there is nothing but the free energy of activation, which is different, not from the free energy change, but how we get this free energy of activation, that is basically the activation barrier. So, for this particular reaction, whether it is the replacement of the water molecule by L or replacement of X by Y, we see that it crosses one small hump and it approaches to some intermediate. That means, when this intermediate is formed, it has sufficient stability and it can be detected at this particular point. So, if some suitable technique is available, we can detect the presence of MXY through some kinetic experiment. Then this MXY further crosses another hump where this particular energy of activation is required to proceed the reaction from the left to right, which is the corresponding energy barrier for the reaction to go from left to right to produce My plus X. So, this is a different form where we do not have any intermediate step, but if intermediate is there and intermediate can be detected, we have the corresponding reaction coordinate for the determination of the formation of My. So, we can have the concentration of the intermediate. So, how we get that? So, we have the corresponding concentration of MXY. So, we can have a corresponding steady state approximation, we call it as a steady state approximation where we consider about the corresponding concentration of the intermediate, in which case we will find that the concentration of the intermediate is assumed to be small. So, that is the corresponding approximation for the steady state, which is reached for the conversion to the product, is assumed to be small and essentially unchanging or not changing during much of the reaction or during the course of this particular reaction. So, these are the things, and we can have certain kinetic experiments to get this kinetic data. So, what are those kinetic experiments? So, in our hand we can have kinetic experiments. So, we should have certain parameters which we can be detected, and in the first case what we can find out from a particular type of kinetic experiment is the order of the reaction. So, in that case we have the concentration of the metal ion, the concentration of the ligand and the concentration of the metal complex form, and if we have the corresponding reactant concentration. So, how we find out the order is basically depending on the power of the reactant concentration. So, how it is dependent on the rate of the reaction. So, power of the reactant concentration if it is the ligand substitution reaction on the ACO complex, it is the concentration of the ACO complex in the differential equation, power of the reactant concentration in the differential equation that describe the reaction. So, if we have some power dependence on the reaction, then how this power is related to the corresponding reactant concentration, and that will tell us the order of the reaction. Then once we know the order of the reaction, then we can find out the rate of the reaction or the rate constant we can determine. So, the rate constant, how quickly the reaction is taking place, that means the speed of the reaction. So, the speed of the reaction we can determine, and then how we find out the corresponding hump, that means the barrier of the reaction what we want to cross is therefore the free energy of activation. So, we have the free energy of activation and we will follow the Arrhenius equation, and that Arrhenius equation will tell us that the rate of the reaction, that means the speeding off of the reaction can take place at every 10 degree centigrade temperature change to double to triple. So, the rate we can increase in that order in most of these reactions. So, how we can find out the free energy of activation? We can find out by measuring or studying the reaction at different temperatures. So, study the reactions at different temperatures. That basically gives us the corresponding free energy of activation, and then we can have another important parameter that we can determine is the heat of activation. It is the free energy, and we all know the free energy, the delta G, the change in free energy has two components. One is the delta H term, another is the T delta S term. So, the enthalpy or the heat term or the delta H term is the corresponding thing what we can find out. So, enthalpy or heat of activation So, heat of activation also we can determine from this study, and lastly once we can have this enthalpy, we can also determine the entropy of activation. So, if we determine all these together, then we can find out, because in some cases also we have other dependencies also, that means the pressure dependence. If there is a change in the pressure while going from left to right, we get the corresponding pressure dependence of any particular reaction. So, if we get all these values in our hand and we can further interpret all these data, so we can have the interpretation which gives us the corresponding reaction mechanism, and along with the corresponding energy surface of the reaction. That means we get the corresponding energy surface. So, depending upon the corresponding rate of the reaction rate constant, when we find out, we have the speed of the reaction, because we find that while we go for the corresponding substitution of the water molecule by some ligand, we see that in some cases the speed of the reaction is very high, and immediately we can substitute all the water molecules by some these ligands. So, we can have, depending upon the corresponding kinetic parameter, we can have the thermodynamic terms So, the thermodynamic quantity for the reaction and the kinetic quantity for the reaction is of two types. So, in terms of the corresponding K values, once we face the corresponding formation constant, if the formation constant is pretty high, the magnitude of the formation constant is pretty high, we can say that the corresponding stability of the complex is also very high. So, we talk about the corresponding stability of the complex. So, one can be very stable, very much stable, or have a high stability, and one can have the low stability for the corresponding thermodynamic parameter depending upon the K value. Similarly, for the corresponding substitution reactions, how quickly the corresponding species is reacting with some other ligand, we can have two types of these complexes. One can be inert complex and another can be labile complex. So, we can have these two terms for the thermodynamic stability and instability, and the kinetic term we can have the inert form and the labile form of these complexes. So, we find that when we talk a particular compound as the inert complex, which is a particular metal ligand assembly or species that are unstable, but survive for minutes or more. If in solution a transient species is formed and has some survival time of a minute or more, we can consider that particular compound is inert. But when this particular compound is react more rapidly than inert complexes, we call them as a very labile complex. So, some of these water molecules which are surrounding the metal centers or the corresponding aqueous complexes. So, from the periodic table, depending upon the different metal ions, we can have the corresponding rapid exchange of these water molecules, because these water molecules can go from the bulk, that means from the reaction medium, from the surroundings, and then it can go and bind to the metal ion. So, depending upon the charge of the metal ion and its size, the corresponding size of these metal ions, the rate of this substitution reaction can also take place, and most of these aqueous complexes are labile in nature if they are from alkali and alkaline earth metal ions, but for some transition metal ions we will find them as their very inert complexes. So, we have two types of these complexes, and while checking this reactivity of these complexes, we will find that there are the reaction types. So, while talking about these inert and labile complexes, but before proceeding to that, we will find that what are the different reaction types we can consider. And while we will talking about the substitution reaction, that means one ligand is getting substituted by the other. Then the dissociation reaction means the ligand is getting dissociated from the metal environment. Then the addition reaction, that means if this is the corresponding opposite reaction of the dissociation, that means we can adapt one particular ligand to the corresponding species. If it is Ml6 type, after dissociation we get Ml5 compound, and then after addition we again get back the corresponding Ml6 or Ml5Y type of compound. Then there are something which we consider as the redox reactions, that means when the metal center has surrounding ligands, that means Ml6 species is there, but it can transfer one electron to some other species or it can accept the one electron to it. That means the redox reactions can take place. So, if we have Ml6 which is 2 plus, so apart from this ligand substitution, ligand dissociation or addition reaction, but also if it goes for one electron elimination or one electron loss, then there will be something, that means some other species should be available which can take up this electron. So, some other species which will be available in the reaction medium, or it can be simply the electrode for any electrochemical system like cyclic voltammetric system or the coulometric system, giving rise to Ml6 3 plus, and this electron transfer can take place between these two species which is Ml6. So, both of them are Ml6, but only change in the corresponding oxidation state of the central metal ion. So, we get the redox reactions, and for that redox reactions we can have all these values whatever we are seeing for the corresponding substitution or the addition or the elimination reaction for the metal complex, and then we will find some of these reactions where the coordinated ligand which is bound to the metal center is undergoing some sort of reaction, that is some organic transformations or some redox reactions or any other type of reactions or some addition reactions on some coordinated ligand which is being facilitated due to the corresponding reactions with that of the metal center. So, we find out that the equilibrium constants for substitution reactions. So, the thermodynamic parameter what we are talking about is the corresponding determination of the equilibrium constants if we consider that the reaction is taking place for the corresponding substitution reactions. Then we can have the kinetic versus thermodynamic stability of the metal complexes. So, the kinetic lability or inertness and thermodynamic stability or the corresponding instability or the opposite of that stable compound of these corresponding metal complexes can be classified in terms of two different terms. One is related to the kinetic term and another is related to the thermodynamic term. And one such substitution reaction is very easy, or very first substitution reactions we can measure for measuring the rates of water exchange reactions in aqueous metal ions. So, sometimes if we can monitor it by some NMR technique or in some cases by isotope effect, that means the water molecules which are being utilized, they are isotopically labeled, that means O17 or O18 of water molecules can be labeled, and we can find out the corresponding exchange reaction with that of our parent aqueous complexes. So, we find that we get two different types of these compound, one is labile and another is inert. So, how we get this particular reaction for this, that if we talk about the substitution reaction, and that substitution reaction what we find for particular copper compound which is hexaaco. So, we have in our hand the cupric copper, copper in +2 oxidation state, which is blue in color, and when we add ammonia, the incoming ligand for the substitution of these water molecules, we find that immediately 4 ammonia molecules can react quickly with this copper center, giving 4 NH3 whole 4 H2O whole 2 plus with the removal of 4 water molecules which were already bound to the metal center. So, this blue color is getting intensified and which is much more intense blue. So, if there is a change in the corresponding lambda values, a slight change in lambda values with a change in the corresponding epsilon value, that means the intensity is changing, the molar absorptivity is changing, that means the epsilon max is changing. So, by looking at the corresponding lambda max for this compound and epsilon max for this compound, we can monitor the corresponding formation of this particular reaction very quickly. So, with time, if we can monitor the corresponding growth of this particular lambda max value for this tetraamine diaco compound of copper, we can find out the corresponding rate of the reaction. So, this particular reaction is a very first reaction. So, immediately this reaction can take place with some time which is some milliseconds only. Similarly, if another color changing characteristic reaction which immediately shows us the corresponding ligand substitution reaction for these water molecules occupying the octahedral positions around the iron in the ferric state is that, and it has a pale violet color. So, very pale, which is very light color, very pale violet in color, which when reacts with thiocyanate anion, and this reaction is in true sense is reversible in nature. We get with the attachment of one thiocyanate group to the iron center with replacement of one water molecule with the elimination of that water molecule. So, there is a characteristic color change if we get attachment of only one such thiocyanate group to the iron site, that basically gives us the corresponding reaction for that, and this red color formation is very fast and we get this sort of reaction or the previous reactions. These are very fast reactions. These are very fast reactions. So, this particular compound and this iron compound, both of them are ACO compounds. So, ACO compounds having a particular electronic configuration which is 3D9, this is 3D9 and this is 3D5. So, these two electronic configurations can tell us they have very first reactions for ligand substitution reactions, therefore, they are kinetically labile complexes. So, the complexes which we are talking here, they are labile in nature. So, for such reactions what we find that if we just start from the solid compound like ferric nitrate, having 9 water of crystallizations, that ferric nitrate when we make an aqueous solution it gives us FeH2O whole 5 OH 2 plus at a particular pH value, otherwise it is all hexaco plus H plus, which is slightly yellow in color, and this basically gives us Fe hexaco 3 plus, which is almost colorless or very pale violet. So, this particular one, so if we just go for this is a typical acid base type of reaction. So, on the complex also we find some acid base type of reaction, because the water molecule which is bound to the corresponding ferric center, this is ferric center, so iron in +3 oxidation state. So, it is polarizes the corresponding OH bond, and the pK value of this particular water molecule is getting lowered, and we get for the corresponding deprotonation, and proton is being lost from the medium, and we get the corresponding species in this form. So, it is the some sort of acid base type of reaction, and when it reacts with say some chloride ion, when the chloride ion is supplying to these, so we get another compound, because most of these compounds what we are talking over here, they are all labile compounds. So, here also we have again H2O pentaaco, and one water molecule will be replaced by the incoming Cl minus. So, this is basically a substitution reaction using Cl minus with the elimination of one water molecule, which is again going back to the same color, which is yellow. Then if we can add some other anion which is highly charged, the phosphate anion. So, when phosphate anion is added, we get FeH2O whole 5 PO4 in electroneutral form of the ferric ion, and which is again colorless plus removal of this chloride ion. And what we have seen in our previous reaction, that this particular species is reacting with thiocyanate. So, at this particular point the thiocyanate is forming strong bond with the iron side. So, if we had thiocyanate anion over here, we get the red compound FeH2O whole 5 SCN 2 plus removal of the phosphate anion part, and this further can react with fluoride anion, unlike this chloride anion, but it can have stronger binding affinity. So, you have FeH2O whole 5 F 2 plus SCN minus. So, we have given some examples of these metal complexes and their corresponding ligand substitution reactions one after another. And how we get these reactions, because if we can monitor that what is forming over there and whether some intermediate is forming during all these reactions. So, if we are able to monitor the corresponding lambda max values, that means the UV visible spectra for monitoring the formation of the different species, we find that all of these compounds are labile in nature. That means, the ligand exchange reaction takes place at the time of mixing of the solutions. That means, whenever we add fluoride to this particular solution, the thiocyanate will immediately kicked out from the medium and we forming the corresponding fluoropentaaco iron 3 plus compound. So, at the time of the mixing, this is forming. So, the labile complex, therefore, we can define as the Nobel laureate Henry Tauve's definition. So, Tauve defined this labile complex is that when the reaction half life for these of 1 minute or less. Reaction half life is nothing but is the time of disappearance of half of the initial compound. So, time required to disappear half of the initial compound, half of the initial compound. So, when the reaction half life is 1 minute or less, we get the corresponding compound as the corresponding labile complex. So, we just can have the corresponding definition for this labile will be in our hand. So, not only this ferric ion, but several other compounds in class 2 oxidation state also. The transition metal ions are moderately labile, particularly the D10 when we do not have any ligand field stabilization energy for mercuric ion or zinc 2 plus ion. So, if we have water molecules surrounding this mercuric ion or zinc 2 ion, they exchange very rapidly with the bulk water molecules or some other ligand groups also. So, they are the good examples of labile complexes. But the corresponding compounds of other groups, that means the strong field D3 and D6 octahedral complexes which are having large crystal field stabilization or the ligand field stabilization energies of -12 DQO in octahedral geometry or -24 DQO in typical octahedral geometry, they provide something where the compound is not reacting very fast. They are called inert or robust compound because they will react more slowly. So, if we are able to make any cobalt compound in class 3, that means we have prepared hexaamine cobalt 3 compound, and definitely it can react with the acid to give you the corresponding hexaaco compound of cobalt in the trivalent state. So, the thermodynamic stability of this compound is there, but its reactivity pattern is different and it will not react easily with the proton available in the medium. That is why it can be easily crystallized for some time. That means, if the solution stability of the compound is there, then only we can crystallize in the solid state, otherwise that compound will decompose in our time. So, increasing the LFSE values improves the inertness. So, for these two, that means these D3 and D6 octahedral complexes, the LFSE values are there, LFSE values are pretty high, that is why it has the corresponding inertness into the system. And compared to the first row transition metal ions, the second row and the third row transition metals are generally more inert. That means, we know the corresponding splitting is more, that means the ligand field splitting is more. So, if we move from iron to ruthenium to osmium, similarly from nickel to palladium to platinum, we will find that both ruthenium and osmium as well as palladium and platinum can show more inert complexes. So, when we study the kinetics of these complexes, we will find that the good choice would be the compounds from the second and the third row elements. That means we can immediately find that the ruthenium and osmium cases, or for palladium and platinum cases, we can measure the corresponding rate of the reaction very easily, because most of the compounds available from there are inert in nature. So, we will talk about the different associative versus dissociative reactions. Before we finalize this thing, that means we go for these associative and dissociative reactions after completing the corresponding reaction, when we consider this as how we get these inert compounds. So, the inert compounds are nothing but they are reacting slowly. So, inert complexes are those which react more slowly, and we also call them as the Rover's compound. So, we have, apart from the corresponding stability in terms of the corresponding thermodynamic term, so the D8 configuration, the 3D8 configuration in square planar geometry, such as tetracyanonickelate, potassium tetracyanonickelate or ammonium tetracyanonickelate is there. And if we consider that we just like water exchange reaction, if we can also monitor the exchange of these attached cyanide groups with the labeled cyanide, where carbon is radio labeled with 14 carbon 14. So, with this, what we will find that this substitution for this radio labeled cyanide can take place, but more slowly, with the elimination of 4 normal cyanide, and in this particular case the half life as per Henry Taube's definition is less than 1 minute. So, this particular reaction is also very fast. So, we have the exchange. So, this exchange, what is taking place, the cyanide exchange is quite rapid. It exchanges rapidly. So, at temperature of 25 degrees centigrade, utilizing the metal ion and the ligand concentration at 0.1 molar, we find that the corresponding T half value is less than 1 minute, and it is basically giving the reaction, it exchanges quite rapidly, and therefore, we consider this as a labile complex. So, we find that this particular one is for something where this Ni2 plus is giving us a square planar complex, and this is basically a stable complex. So, from the thermodynamic point of view, we get a stable compound, which is a very stable one, we all know. But when we talk about the corresponding exchange reaction with say radio labeled cyanide, we find that it exchanges quite rapidly, and from kinetic point of view it is a labile complex. Similarly, when we find that in case of another cyanide complex, which is hexacyanochromium, which when exchanges with 4 radio labeled cyanide, we get 14 Cn whole 6 3 minus plus 6 Cn minus, and in this particular case our T half is 24 days. So, this T half basically tells us that this particular compound which is getting exchanged with this 14 Cn minus is now inert, and that we have seen also that for a particular type of electronic configuration which is 3d3, here it is 3d8. So, for 3d8 in square planar geometry, what we expect that it also can give rise to some inert compound, but this particular inert compound we are not getting in case of nickel, but expectedly we can have this for palladium and platinum compound, but in case of chromium for the first transition series element it is kinetically inert compound. So, we get basically a compound like this which is inert. Similarly, another example we can have, and what we have seen just now also, that this fluoro compound also we have seen that this is a labile compound because it exchanges quite rapidly. It removes the thiocyanate group from the coordination sphere of the iron, but it has large equilibrium constant of formation, because when we find out the corresponding K value, it has a large value of the corresponding equilibrium formation constant. That means it is thermodynamically stable, it is not unstable, it is thermodynamically a stable compound, but it is kinetically labile. So, what we just told you also, that when we have the corresponding species, that means hexaamine cobalt 3 plus, which when reacting with acid which is protonated one H3O plus. So, this proton will go and bind with these ammonia molecules, and this particular one when react with ammonia molecule, so is unstable in acid medium. So, it is unstable in acid medium, that means thermodynamically, since this is stable, but this is unstable. So, these two things are going in some cases not in the same direction, but what about its corresponding kinetic term? It is unstable in acid medium, that means if we put in the acid medium, it definitely can go for the corresponding decomposition to give us the corresponding hexa-aco compound, with 6 ammonium ion and delta G0 is negative, that means it is spontaneous also. So, the formation of this particular one, that means slowly it can form the corresponding hexa-aco compound, but it is unstable in acid medium, that means it gives us that idea that it will decompose slowly with the acid, but the reaction is very slow. Reaction is very slow, that means it is reacting slowly with the acid available in the medium. That means this particular compound which is in 3 the 6 electronic configuration is kinetically inert. It is unstable thermodynamically, but kinetically it is inert. Okay. So, next day we will just consider about the other reaction mechanisms. Thank you very much.